Yeah, as Samir said, I'm going to talk about computer science data structures. So who here is interested in doing computer science in college? All right. But essentially, I guarantee you, once you start doing interviews, 30% of interview questions revolve around these two data structures I'm talking about. So the first one we'll talk about, they're called stacks. So first off, who knows what arrays are? Or come across them in their coding? All right, so arrays, essentially you want to think about them as like a list. You guys know what variables are? Right, so essentially you have a list of variables that you can just store and everything has you know where they're located because they're indexed. Does that make sense so far? Yeah? You gotta say something. I gotta get some response, guys. Yeah? All right, good, thank you. So a stack is essentially a list, but how it's structured is that you can only put things on top, right? For example, a stack of books, you only stick things on top of it, right? Another good idea to think about this as is when you wash dishes, right? If you have a stack of dishes, you're not going to take the bottom one out underneath it and wash it, right? You're going to take the top one and wash it. Whenever you put one on top, you take the top one off. Does that make sense so far?
Yeah.
Yeah? Okay, thank you. So the stack has the only elements you can access is the top one, right? As I said, this is a plate of dishes or a stack of books, right? And then they're sorted as whenever you put them in. This is pretty intuitive so far, right? Yeah? Okay. It's the last element in and first out. As I said, top one goes in, top one goes out. But then you can't access anything in the middle, right? Does that make sense so far? Because you're not going to take out a middle plate, right? Yeah. That's essentially what stacks are. And who can think of an example that you guys use stacks every single day, especially when you use your computer? Can you think of an idea of how this is applied in your everyday life?
You have to start the computer first, and then...
No, an actual implementation.
Oh.
You use it every day, I guarantee you. Can you think of something where you go forward, and then once you want to go backwards, you take the forward one off? It's a big clue. No? Any guesses? No? All right. Oh, dang it. I won't say it. But essentially, web browsing is a really good example of stack, right? So you go on a website, right? If you're on Google and you search it STL, and you go to your STL website guide, and you go to table contents, and you go to the stack page, because stack is a STL implementation in C++. And then you go backwards, right? The current website you're on, no? Too high level for this? All right, imagine you're on YouTube, all right? And then you go to a certain YouTube video, and then you want to go backwards, right? This is essentially a stack. Your YouTube video that you're currently on goes on your stack, and when you go backwards, you remove it. You go back to your normal YouTube page. Does that make sense?
Yeah.
Yes?
It's okay if it doesn't.
It's okay if it doesn't. You could ask me questions. Don't forget. I'm trying to teach you guys here. Yes, questions?
So you said you can't access anything in the middle of a stack,
Mm-hmm.
but for the example of a YouTube video, you can go to your history.
What's up?
You can go to your history, right?
That's a little different. I'm going to talk about history later on, but that's not exact. When you click on it, essentially how that works is not a stack in terms of actual web browsing, right? You know what I mean? But accessing your history is a little different. Any other questions? I saw another hand. No? Okay. So I'm going to move on to the other really important data structure. They're called queues. Essentially, you can think about them as a line, right? When you're in line for movie theaters or anything, the first person who goes in gets to go out first, right? So you get first person, second person, third, fourth, fifth, right? And then they come out in that exact order. You have the front and the back. And so, again, elements are sorted in certain order. First element in, first element out. You can only add to the back and then remove from the front, which makes sense in terms of a queue. Right? Makes sense so far? Mm-hmm. Okay. So, can anybody think of an example for how queues are used every day? You also use this every day when you surf the web. Anybody think of an example? Anybody? No? Yes?
When you're on a music player and then you make a queue.
Sure, yeah, that works, right? Because you can only, the only first one gets access, right? But a really good example of how queue is used is your browsing history, right? So, for example, if you clear out your history, you got nothing, right? But when you scroll on a website, it gets pushed on, and then and essentially, that's like the oldest one, and you keep adding on newer and newer ones. The oldest one will always be removed because it's the first one in there. That's how your history works, especially for like Google Chrome or something. Does that make sense so far? Any questions? Do you guys understand like the premise of this stuff? Because I'm going to move on to like the applications of it pretty soon. Any questions?
So you mentioned how the stack was like an array.
Yeah.
Wouldn't an array be more like a queue though?
No, I'm just saying they're all like lists, right? Because a lot of people don't understand, they haven't had like experienced arrays or lists yet. So I'm saying, in general, these are just lists that you can use, and their applications are different. Any other questions so far? No? All right. I'm trying to make this engaging with you guys. Okay. Fine. I'm gonna just show you guys like a quick demo of like how queues and stacks have been used. So this is using. So this is a project I worked on using queues and stacks. I forgot which version it is, but essentially everything that's marked red are like the paths that Pac-Man took before it found its final path. For example, you can see it's not going to any of these dead ends because it knows it's already searched there. Right, and its end goal is the food right here. Yay. Sounds cool. But yeah, like that is a really good example of either crap. I think I'll use both depth first search. Okay, so what I'm going to is like search algorithms, which is essentially what you learn in actual artificial intelligence. Because back in the day, what they used was like tree searches, right? For like games or everything. Like you do tic-tac-toe, right? You have this tree search where you want to figure out, you have the computer figure out what's the next move I want to do, right? If a human does this move, the computer has these sets of moves. If you're confused why this only has two, it's because it takes into account rotation, right? This thing is the same thing as this over here, over here, over here. Does that make sense so far? Everything good? Okay. So this part's gonna get a little more complicated, so slow me down if you need me to. So the first application of like stacks and queues is called the search of breadth first search. All right, so essentially how it works with breadth is when you have a tree, you have like your main top node, and then you have your root nodes, and then you have your leaf nodes and everything like that, right? So that first search goes by levels. This is level 1, 2, or 3, or in case of the 3 signs, it'd be level 0. Don't actually forget I said that, don't confuse you anymore. So depth searches by level, right? So it checks the first level, checks if like your end goal is there, and then your second level checks if its goal is there, and if not, you keep going down, right? Does that make sense so far? It checks by levels. Yes? Any questions? Some of you guys are kind of bored. Yeah?
Can you give us an example of that?
What do you mean, like example?
Like a Pac-Man thingy?
What's up?
Like a Pac-Man thingy? Does it use the breadth first search?
Can we show you like a path?
The Pac-Man thingy?
Oh, the Pac-Man thingy? Okay, yeah.
Does it use that breadth first search?
Yeah. That's kind of really hard to show, but
Maybe we should Google.
actually, it's gonna take me a while to pull that up. So if you want to see it later, I can show you guys. But yeah, let me just go through like a really quick example on this. So this is first in, first out queue, which I probably should have put the queue part in, but you guys know which data structure this uses. If it's a first in, first out.
Queue.
Right. Even if you didn't see this, you would have known, right?
Yeah.
Okay, good. So let's go through a really quick example so you guys can see how it works. So if I want to get to F, it's going to check A first, right? And then how it works is it goes by level from left to right. So which node is going to check next if A isn't the goal?
B.
Right. And since it goes by level, what goes after B?
D.
Goes by level. It checks the same level
C.
first. C, right? Okay. So, right, it checks if B is a goal and then checks if C is a goal. And then there's this queue that it uses to like determine which node to expand at, and it'll be put in that order. So B and C goes in that order, and then checks the next level, right? But in which level would it check? Which letter would it check first?
B, little D.
Wait, so it checks the B and expands to which two letters?
D
D,
and E.
All right, and which one goes first?
D.
D.
Yeah. So it checks if D is goal and then checks if E is goal, right? And that's the end of the tree. So it goes back up to C afterwards, right? Because it goes, well, it expands to C1, right? The C is already been checked. So, and then it expands to F and you see it's a goal, right? Does that make sense? Everything works out so far? Makes sense? Yes? Questions? Questions are really important because I feel like some of you guys don't understand this. Yes?
Quick, sorry, put on mute.
Oh. No questions? All right. So we're gonna move on to the next one, I think. Yeah. All right. So depth first search. The difference between depth first search and breadth first search is breadth first search goes by levels. Depth first search goes all the way down one side of the tree before it comes back up. Right? It means depth. So all the way down. Breadth is levels. Make sense so far? Yes. Yeah. Okay. So if it goes last in, first out, which type of data structure does it use? There's only one other one.
Stack.
Correct. All right. So bear with me for this, with this example, but it's called. This is all right. I'm gonna try my best because it's kind of small. Can you guys all see this? All right. This is like the best example I can come up with. So it goes by like it goes down one side of the tree first and then slowly expands down. So first it checks A. Is that the goal? It's not, right? And then it checks B, and then expands from B down like goes down one side first, right? So you can see it expands at B and expands at D, right? And then checks if H and I are goal states. If not, it goes to the other side of the tree, and so on and so on. Do I need to like write this out, or do you guys understand how it's going? Yes, yes. It's pretty simple, right? But yeah, dude, that's like honestly all I have. You have any questions about this stuff? Yeah.
Yeah, so when it goes down one side, then does it go back all the way up?
No, so it goes, like for example, this example here, it goes straight down to H and then checks I, right? But you still have this branch of the tree that hasn't been explored yet, right? Because you want to keep going at the deepest level on one node. So this is node that you're still at, but you still haven't expanded on this side because this is deeper. This is more like this is deeper down in the tree than this one is, right? You want to check everything on the bottom level, like closest to the bottom level first before you go back up.
But then how does it do the other side? Does it?
It goes back up here, right, and then checks the, like, it goes by like left to right. Does that make sense? It's like it checks this side first,
Yeah.
and then it'll see like deepest side on this side. Does that make sense?
Yeah.
Okay. Yeah.
Wait, so if it hits, if so one of the nodes is gold, then it just stops there, or it goes down?
Once it finds its goal state, it stops.
Yeah.
What are the applications of these searches?
So as I said before, like game trees, right? For example, the one I showed you with like tic-tac-toe. If you want to like program like a really simple like, computer, you would use game trees, and it'll determine all right which for game trees how it would work is that you would assign like a point value to every move, and you'd get more positive points if you were going to win versus where you're not going to win. So if you want to code like a pretty basic computer program to play against, that's what you would use, like a tree search, where it would like map out all possible moves you could make and keep on going down until it sees as a win state. Does that make sense? Any other questions? Yeah.
Are there any other applications?
Mostly like depth first search and breadth first search are used for tree searches or graph searches. And anything you think of like as like using like paths or like moves, where everything's like distinct moves, then you could use these searches on. But mostly if I've occurred is like game trees, because that's what I've been studying, and like interview questions, right? Any other questions? No? All right, Samir, that's only all I got.